Hi guys, and welcome back to our next lecture as we continue to talk about simple binding phenomena and protein ligand interactions. Now, I left you guys the last time thinking about sort of the simplest case of a protein binding to a single ligand in a reversible way, right? That's what we sort of spent most of our time talking about. So the sort of simple binding phenomenon that would be described by a scheme that would look something like this: protein plus a ligand A in equilibrium with the protein ligand complex PA. We talked about thinking of that equilibrium constant as a dissociation constant, so the inverse of the association constant. And I pointed out that the degree of binding, which expresses or captures or quantifies the total moles of A bound relative to the total amount of protein, is simply equal to, we went through that simple derivation, the total amount of A in solution divided by the dissociation constant plus the total amount of A present. Okay, so we went through and we talked about some of the plots one would use to take data like this and then extract out of it these parameters we might care about, like the dissociation constant. And then I went on to talk about a simple case of, and that was fairly relatively straightforward, right? In how you would use that simple or direct binding plot, or that titration binding plot. I pointed out the scatter plot. We're going to come back to the scatter plot a little bit here later in this lecture, and some of the problems that it presents if it's used or misused. But then I ended with a sort of the next more complex case, right? Well, what if our molecule could bind more than one ligand, right? And let's just say it's the same ligand, but we've got two binding sites, right? That's the next most complex case. And I didn't write it out explicitly last time, but I'm going to write it out explicitly this time. So what if we had a situation where we had protein combined a mole of A to form a PA complex? What if it combined another mole of A to form, say, a complex PA sub 2, right? Well, I could say I've got two different dissociation constants here, say, right? So we'll call this one here K1, K sub 1, this one K sub 2. And remember, we're thinking about these as dissociation constants, right? Okay. And I pointed out that there's a relatively trivial case for thinking about something, a situation like this, if K1 exactly equals K2. And if these sites don't interact in any way, there's no coupling, there's no linkage. We'll come back to that idea again later. So they're fully in, if the equilibrium constants are exactly the same and the sites are independent, right? I pointed out that the degree of binding for this case is trivially can be generalized, or I should say for this particular case, would simply be just like the simple single site binding, but it's multiplied by 2, right? So it'd be 2 times A divided by the dissociation constant plus the concentration of A. And more generally, for any situation of a binding a macromolecule that had multiple sites, say, to N, assuming the binding constants are all exactly the same, the sites are all independent, this can be generalized or is generalizable to a situation, or is generalizable to that stoichiometry value simply being multiplied by that sort of simple binding equation, right? Okay, that's great and all. The problem now, one of the problem, the next wrinkle that we have to grapple with is that does happen, right? Where all the binding sites are exactly the same, but a far more common situation in a scheme like this is what happens when K1 does not equal K2, right? We dealt with that case the last time. What happens now if the binding constants for a 2-site binding macromolecule to the same ligand, let's say, just keep it simple, don't have the same dissociation constant. They're still independent. There's no thermodynamic linkage, but they don't have the same affinities. Okay. There are two different ways to think about that situation, two different models, turns out, that you can derive or you can proceed from. You ultimately come to an expression for the binding equation that is the same, but there are some differences depending upon how you set up the initial assumptions. So let's go through that, because this illustrates something really kind of important. And I'm going to write this out in a slightly different way now. So let's write this. We're going to assume that these binding constants aren't the same, but I'm going to write this in sort of two steps now for this first attack on this problem. So we're going to say, what if you have our macromolecule P plus A with dissociation constant K sub 1 that makes PA, right? And then we could take some PA, bind some more A, right? And there's our second binding event with our second dissociation constant, PA sub 2, right? All right. So the first question is, what's the degree of binding expression look like for this? Remember, the degree of binding, right, is just equal to the total moles of A bound divided by the total moles of P, right? Okay, so what would that look like? Well, that's easy, relatively easy, right? So we know that's what that has to be. So let's see, moles of bound A, that'd be concentration of, that's the concentration of our monomolecularly bound complex, right? Plus 2 times the concentration of our dimolecularly bound complex, right? There's 2 A's bound. Where'd the 2 come from? That makes sense, right? PA sub 2, gotta multiply by 2, right? Okay. Divided by concentration of unbound P plus the concentration of PA plus concentration of PA sub 2, all the species of bound and unbound P in solution. All right, so that defines our degree of binding. Okay, so we want to go through this exercise of how do we substitute stuff into that expression to get a degree of binding in simple terms with as few variables as possible that we could actually use, right, say to fit data. All right, well, let's rearrange these expressions a little bit. Let's take K1 here. At K1, and we're going to define it, right? Concentration of P, concentration of A, divided by concentration of PA. And we'll say K2, right? Same sort of thing, is simply equal to concentration of PA times the concentration of A, divided by the concentration of PA sub 2, right? Nice, straightforward. Okay, well, we can rearrange this, because remember, the name of the game in these sort of derivations often involve, at least to begin with, reducing the number of variables. We got a lot of variables, so let's see if we can combine expressions and make this a little bit cleaner. So let's rearrange that expression for K1 first. That's easy. Solve it for PA. So concentration of PA has to simply be equal to concentration of P, concentration of A, divided by K1. We can do the same thing with this guy over here. We can solve this one for the concentration of PA2. You'll see why in a moment. Solve this one for the concentration of PA sub 2, right? That equals concentration of PA, concentration of A, divided by K2. See where we're going? See what we can do? Now we can take this and we can go, ooh, what if we substitute that in there? Okay, that's going to get rid of a variable for us. So if we do that, we now get an expression for the concentration of PA2 that simply equals concentration of P, concentration of A, divided by K1 times concentration of A divided by K2, right? That's cool. Let's simplify that, baby. We can make that look a little bit better. So concentration of PA sub 2 simply equals now concentration of P times concentration of A squared divided by K1 times K2, right? Cool. That's easy. All right. But we've now got our concentration of PA2 in terms of P and A, free P, total A, K1 and K2. Take that guy. We've got that definition for PA. What if we take now both of those expressions, right? Our expression for PA, right? Because remember, it's the degree of binding expression that we want to work with. We can take this definition, we can substitute that in here. We got an expression here for PA2. We can take this baby here. We can substitute that in up here too, right? That's kind of useful, right? Because now I can reduce these other two expressions allow me to reduce that other expression to one that only has a couple of variables to it. Oh, all right. Let's try it. Let's give that a shot, see what happens. All right. So if we take this expression for the degree of binding as we just defined it, and now go substitution happy, we're going to write that baby back out. It's going to look something like this. And let me just rewrite it for you. So we've got the degree of binding equals the concentration of our bound states, right? PA plus concentration of PA sub 2. Oops, dropped a term. 2 times the concentration of PA sub 2 over concentration of P plus concentration of PA plus concentration of PA sub 2, right? You guys remember that? Yeah, so I got our terms there. All right, now let's do that substitution trick. All right, so we've got this definition here for PA. Let's substitute that guy in. So our degree of binding now is going to be equal to concentration of P, right, times concentration of A divided by K1, all right, cool. And we can go 2 times our concentration of PA2, there it is right there. So that's going to be 2 times concentration of P, concentration of A squared, right, divided by K1 times K2, cool, divided by concentration of P plus concentration of P, concentration of A over K1 plus concentration of P, concentration of A squared over K1 times K2. Well, right out of the gate, you should see something that you can do here, right? We can basically take that expression like, well, there's some terms we can get rid of. We can get rid of that guy, that guy, that guy, that guy, that guy. He's in all the terms. So that goes away. That's cool. So I can rewrite that now. It's going to look a little like something like this. Degree of binding now is going to equal concentration of A divided by K1 plus 2 times concentration of A squared over K1, K2 divided by 1 plus concentration of A over K1 plus concentration of A squared over K1, K2, right? Cool, neat, awesome, right? Get a common term there, do a little multiplying through, a little simplification, and we get an expression for the degree of binding in this case. That looks like this. K2 concentration of A plus 2 times the concentration of A squared divided by K1, K2 plus K2 concentration of A plus concentration of A squared. So that now is our degree of binding expression that describes binding of a ligand for this scheme with K1, PA, PA plus A, K2, PA sub 2, right? Not quite as simple as we had before for the single site binding, but you know, it's going to be a little more complicated, but it's not too bad, right? Fairly straightforward. And look at the terms, right? The terms of this expression are essentially just like we got before. There's no additional variables. The protein concentrations are not in there. This expression is just a function of the binding constants, these two different binding constants, right? K1 and K2, and the total concentration of A. But there's a problem if you really think about this, right? And if you think about what this scheme, the assumption that's kind of built into the scheme, the way I've written it here, right? Why would the ligand bind to the first site before it binds to the second site? I mean, if K1 was a whole lot smaller than K2, so the binding constant, as we've written it here, K1, if it was a whole lot smaller than K2, so that binding event was just dramatically tighter than K2, maybe that would happen. But that wasn't an assumption that went into this model. This in principle, K1 and K2 could differ by a factor of 2, right? But the way this is written and the way the derivation runs, it sort of assumes that K1 binds before K2, and that's not going to be true, right? So what does that mean? Well, if you think about it, what that has to mean is that these binding constants, K1 and K2, in this expression, the way I've written it, cannot be true binding constants, right? They're something else. They're related to binding, but they're not true binding constants for the two different sites. In fact, the fact that they're not, they get a particular name. These binding constants in a binding derivation that is configured this way, this kind of model, these are known as macroscopic. I'll explain why later. Okay. So the macroscopic binding constants related to binding, and you could take that expression and you could take some actual experimental data and for a molecule with 2 binding sites, and it would fit this beautifully, and you'd get numbers for that K1 and that KT value. But what you haven't gotten when you do that is the true binding constant for each of those sites because of the assumptions sort of built into the model we use to derive that expression. And to illustrate that, we got to think about it a different way.